Hi everyone, I'm Kevin Eykholt, and I'm here to present my work on access control and databases. So just to begin with, web applications are a very powerful way to empower your users and grant them access to online services, so e-commerce, banking. And typically there is some backend database for all of these web applications that stores, it could store personal user information, it could store, inventory lists. And the problem is because these applications are public-facing with lots of data stored within the databases, they become a high priority target for attackers. So for example, in 2014, there was a data leakage. In 2015, another data leakage. In 2016, another data leakage. And so you see periodically that these kinds of attacks just happen year after year after year, despite some of the attack vectors being very simple attacks. And enforcing fine-grained access control can really be done in two different areas. So one of them is you could put them on the database system. So for example, Oracle and Postgres are both examples of databases that allow you to define fine-grained access control within the database. And these usually operate within the context of the connected database user. And the problem with that kind of model is that typically the connected user is not actually the application user. So what you may see is a pool of open connections between the application and the database, and these connections have the ability to access any user's information in order to facilitate this creation of a connection pool. Some of the other issues that you might see is that the databases have database-specific syntax for defining the fine-grained access controls. So for example, if I were to define access control on the Postgres database, I couldn't then go to an Oracle database and use the same set of syntax to enforce my access control rules. And also the syntax tends to be very complicated in that I need to know more than just basic SQL in order to define my access control rules. So an optional solution would be to say that, well, if the connection pool doesn't have the application user context, why not put it on the application server? So there's been a lot of work in this area. Two of the ones I'm going to look at are Clamp and Nemesis. These are ones that are closely related to our work. And they both allow you to define access control policies on each of the tables. Now typically what you'll see with this kind of work is that the application solutions will use what are called database views in order to define their access controls. And the reason they use database views is because database views are a very natural way to restrict users to the authorized portion of the database. The syntax is typically with a select query, so it's also very easy to understand. And an example is, suppose we had a table where we wanted to say customers should only be able to view their own order information. This select query would enforce that, and this current ID may be a wildcard field that gets filled out when the user connects. You can also use this same query in order to enforce a write policy. So you might say that, well, I want it so that customers can only update their own orders. So again, you'd use this database view to enforce this. Now, notice that in order to enforce this policy, I need to have some field within the table that allows me to uniquely map a user to the rows that they're allowed to access. And the problem comes, what if I can't do that? What if there is no, for example, a user ID within that table, or the user ID isn't enough of a context in order to give me that sort of mapping? So an example of that is, suppose I have this policy that I want to enforce. I want to say that customers can only leave reviews for items they have purchased. Now the reviews table may have a user ID field that says that it gives me an idea of who left the review, but the review table may have no idea of what customers have purchased. So using the database view, I might see a view definition such as this, where I need to join multiple tables together in order to get an idea of what customers have purchased and then to authorize the write policy for that table. And the issue with this is that this database view isn't what we call updatable, which is that I can't necessarily do a write to this view and have those writes mapped to the underlying tables because of the presence of the joins between these tables. So we thought maybe the reason that these applications or the application-based solutions didn't really care too much about this was because of the fact that these join queries don't really happen very often in practice. So what we first did was we went and we got 9 open source web applications of varying sizes and varying areas. And we enumerated how many of those tables would require a join policy, either based on the documentation or sort of the implied schema. we found that on average about 21% of these tables would require this definition, which means that if I used previous solutions, I would have an issue where I couldn't enforce or define an access control policy successfully for write queries on 21% of my database. With this problem in mind, you see some people choosing to write their own access control policies. And that's typically where you get into trouble and you see these sort of database leaks. So there was a study done of 396 open source web applications over the course of 5 years. And it found that there were about 269 vulnerabilities. And some of these vulnerabilities are very simple vulnerabilities, such as SQL injection, where with proper access control rules and enforcement on the backend database, you could have avoided these kinds of leaks. And this isn't limited to just open source web applications. As we saw before, Symantec had an issue. Again, this was a SQL injection issue, where a user was able to elevate their access to administrator level permissions on the database. So with these problems in mind, we're looking to achieve 4 goals here for our design solution. First of all, the access control policy should be able to be enforced fully for both read and write queries. It shouldn't just be for write queries under specific conditions. Second, it should be that if a query or the results of a query are made permanent to the database, that those changes are in compliance with the access control policy. It should only ever be authorized reads or updates. It should be compatible with the current architecture, which really talks to 2 things. One is that the way web applications are currently set up, I should be able to put the solution on without any major changes. And it shouldn't be dependent on the backend database. So even if I were to go from, let's say, a Postgres database to a MySQL database, I should still have that guarantee that the queries are going to behave in accordance with the policy. Finally, we want it to be simple. So there shouldn't be this huge amount of documentation that you would need to read through in order to understand how to define your policy and ensure that it's going to work correctly. So our idea was, let's put the solution within the driver. And the reason we choose the driver is because since it's on the application, I can obtain the connected application user's context. I can also intercept all the queries before they're actually executed on the database, and then handle them and make sure that they are in accordance with the policy. So for our work, we had this notion of query safety. So first I'm going to explain what query safety is for our work, and then go into how we ensure that any query that we intercept is safe once we execute on the database. And then we're finally going to look at the performance on 2 different databases, MySQL and Postgres. So again, database policies, we have 2 different database policies. We have read policies and write policies. And remember, policies are just a set of rules of what users can access or update within a table. We might have a very simple policy, such as this one, where the read and write policies are the same. We might have another example where the read and write policies are slightly different. So for example, this one says that you can see all the tables, all the tuples in the table, but you can't necessarily make any modification to them. And finally, we might have a more complicated policy where the write policy contains some sort of join. And with these kinds of policies, we'll say that a query is safe if it allows a user to view and modify authorized tuples in the database based on the relevant security policy. And we break this notion of safety into read safety and write safety. We say that a query is read safe if the behavior of the query wouldn't change if I were to restrict it to operate only on the authorized tuples. So for example, if I have this read policy that we saw before, and in this case, this is if the connected customer had, let's say, the ID of 1, then the query on the left is an example of a read-safe query, because restricting the query to only operate on rows with customer ID 1 doesn't change the results the query would return. On the right side, though, we see an example of a query that's obviously not safe, because this query, if there were rows in the table that do not have customer ID 1, then this query's behavior would change once I restrict it to only return the rows with customer ID 1. Write safety is very similar. So write safety has 2 conditions, though. First of all, that it needs to be read safe, because we don't want to have any sort of data leakage through your write query. Second of all, it shouldn't modify any unauthorized tuples. And modification is both changing the existing ones or adding new ones. And so the query's behavior shouldn't change if we restrict it again to, in this case, tuples that are in the write policy. So another example, we have the write policy, and the query on the left is obviously write safe because, again, restricting it to the authorized tuples doesn't change its result. Whereas the other two queries aren't write safe. The first one's not write safe because its behavior changes when we restrict it to only the authorized tuples. And the second one isn't write safe because it's not read safe. So the inner nested query, the select, we already know isn't read safe from before. So this by definition isn't write safe. So given these ideas of query safety, we then want to look at how do we enforce this through the driver. So the driver will intercept a query before it's executed on the database. And then it'll run the query through a process called read-set intersection. And the result of read-set intersection is going to be a read-safe query. And at this point, we need to determine if the query is a select query or if it's not a select query. If it is a select query, then we know that the query is safe to execute on the database because it is a read query. However, if it is a write query, such as, let's say, a delete, an insert, or an update, then we need to run it through a second process called phantom extraction. And the result of phantom extraction is going to be a write-safe query, or in some cases, behavior that mimics similar behavior to a write-safe query. So read-set intersection takes advantage of a very simple idea, which is that we notice that we can append the where conditions of the policy to the select query's where conditions. And that will ensure that the query only operates on the authorized tuples. The theoretical backing behind this you can find in the paper. So suppose we have this select star from orders. We knew that before this wasn't read safe. But when I run it through the read-set intersection, all I do is I simply add that extra where condition. And I know that this query is going to be read safe. So phantom extraction has two steps. The first step, which was already done, was to transform the query into a read safe query. That's to satisfy the first condition. And the second step is to modify the query so it only updates tuples authorized by the write policy. And then we perform a check afterwards to see if the modifications would still be safe. So we have two different strategies we look at for this one. We have vcopy and no copy. Now vcopy, which stands for view copy, uses what are called temporary tables within the database in order to ensure the safety of a query. The reason we use these temporary tables is to make sure that none of the changes to the database are made permanent until we've verified the safety. Once we have verified the safety, we can then copy those changes into the original table. And vcopy will always result in safe behavior by our definition. So for example, suppose we have a customer with customer ID 1, and they want to issue this insert query. Now this insert query obviously is not safe because that second value 2 does not match their customer ID. So first the driver is going to intercept it, and it's going to copy the schema of the table that's being updated here. In this case, we only need to copy the schema because the insert query doesn't actually rely on any of the underlying information. We then perform the query on this temporary table, and then check with the write policy whether the results of this query are contained within the write policy. In this case, they are not. And so the fact that there was a change based on this policy definition means that the query isn't safe. And so to get safe behavior, what we do is we execute a null query. So we don't make any changes to the database. If we look at a similar example, suppose we have this delete query from before that we knew that was not write safe. We would intercept the query. And in this case, since the delete query does rely on information in the underlying table, we'll only copy the authorized information. And then we would perform the execution of the query on this temporary table, and then check in this case whether the result is safe. Now in this case, since it's an empty table, this is within the write policy, and so this means that we can propagate the changes and remove the row. Now note that we propagate the changes rather than re-execute the query. And this is because we don't know if executing the query on the original table is safe, but we do know that when we execute it on this temporary table, those results are safe. So with vcopy, we note that there are some places that you can do some optimization. And mainly you can avoid the creation of temporary tables under certain conditions. So for example, you might have saw in the delete query, there wasn't really a need to re-execute the policy on an empty table. And one example would be to say, suppose we intercepted the delete query from before. And all we need to do is treat it similar to a select query and append additional where conditions to that delete query. So for example, here's our delete query from before. And we could execute this new transform delete query on the database, and this would be safe according to our definition. So with this in mind, we then went to perform experiments using these ideas of read safety, write safety, and these vcopy and no copy techniques. We created our own custom JDBC driver that implements vcopy, no copy. It also was able to do query parsing as well, so we could do query parsing and the manipulation. And we used the TPCG benchmark for our experiments. This is a benchmark that's provided through the LTP benchmark tool. It has 5 different transaction types. And for those 5 transaction types, we created 2 access roles, and then we assigned those transactions to each of the roles. So for example, this is the policy that we originally enforced. And essentially, like for example, that first row there where it says equals CID, DID, WID, that means that a transaction executed by the customer role can only modify rows where the customer, district, and warehouse ID are matching. And that's because customers are uniquely identified by this triple, whereas managers would be uniquely identified by the district ID and the warehouse ID. So with this access control policy in mind, we then measured the average latency and average throughput. This is just provided by the benchmarking tool. And we wanted to answer 3 questions. We wanted to know when queries in the workload are safe so that they conform to the policy, but we would still need to check and make sure. What's the performance overhead when we implement when we use our solution on a database that doesn't have any built-in access controls? So we're looking at a MySQL database in this case. And in the second case, we want to know how does safety compare to the existing built-in access control mechanism. So in this case, we used a Postgres database with the 9.5 or higher. Finally, we want to know that if there are queries in the workload that are not safe, how is safety's performance affected as the number of queries increase? So for the first question, we did this on the MySQL database just before. And we see that on average, safety has about a 6% overhead. And we consider that, well, we're getting this extra safety guarantee while having a relatively low overhead here. Now, when we switch over to the Postgres database, we see that the safety access controls have comparable performance to the built-in access controls, which is the red bar here. And this then caused us to ask, well, what happens when we change the policy? So previously, this was our security policy. And the thing about this security policy is there's no join queries necessary anywhere in this security policy. And one of the things we wanted to look at was what happens when there's a join query in the policy, because that's when some of the application controls have issues. In this case, what we did was we changed the access control rules for these 2 rows here. Now note that within the benchmarking, all of the customer IDs are positive to begin with, so this doesn't actually restrict any of the access that the manager role has to the information, but rather it ensures that there'll be a join query as part of the policy definition for the table. With this in mind, we then reran our experiments, and we found that the built-in controls suffered considerably. vcopy also has disappeared completely. That's because when you have this join policy, the creation of those temporary tables, especially for something like the manager role, which has access to a lot of information, has really high overhead. When you compare the red line here to the purple line, you see that the built-in controls are an order of magnitude slower than our controls using the no-copy strategy and safety. Now, we also ran a second set of experiments, which was to denormalize the database. So typically, you would normalize the database in order to remove redundancy. And what we ended up doing was we ended up combining a bunch of the tables. And what that does is it removes the join query as part of the policy definition, but it results in a much larger table. Now, when rerunning these experiments, we see that the built-in controls have a much higher throughput before. That's the yellow line there. But no copy, which is the orange line, again, still outperforms it. So based on these, we see that no copy is faster than the built-in controls, at least in the case of Postgres. Now, when we look at the unsafe queries in the workload, we wanted to not change the behavior of the benchmark, but we still wanted to have occasionally there'll be queries that would need to be modified in some way. So we added a random mix of read and write queries to the workload. And we varied that number between 0 to 10% because we don't expect the attacker to have to be a large portion of the workload in this case. We see that vcopy, as we saw previously, is actually very slow, especially as the number of queries increases, whereas no copy has a relatively small change as the number increases. And that in terms of the average transaction rate, the no copy strategy bottomed out at around 350 transactions per second, whereas the vcopy strategy drops very quickly. Finally, looking at the syntax knowledge required, safety only requires the select. So we borrowed from the sort of the database view definitions and reused the selects. And Postgres, on the other hand, requires knowledge of policies, policy conditions, and Postgres roles, how to define those. And finally, we also looked at Oracle. Oracle was the most complicated of them, requiring 4 different things outside of the normal SQL knowledge. And when we look at the lines of code required to define these policies, we see that safety is low at 36. So this is 9 tables within our database. A read policy and a write policy goes to 18, and then you have 2 different access roles coming up to 36. Whereas in order to define a similar policy within Oracle, that required, for us, 544 lines of code. So as we saw before, we took this notion of query safety. We implemented it within a driver. We saw that the overhead for safety on a MySQL database was about 6%. It compared favorably with Postgres on simpler policies that didn't require a join query. And when a join query was necessary, we saw that safety outperformed the existing built-in controls. Safety is compatible with the architecture that we show here. And it does have a notion of who the connected client is. It's independent of the database since it's a driver that exists outside of the database. And when we evaluate it on the unsafe queries, the queries were always changed to be safe, and we saw a relatively low performance drop, at least in the case of no copy. So that concludes my talk, and thanks.
Are there any questions? So let me ask you a question. So in the during the PC meeting, so one of the questions that came up was advanced database features like triggers and things like that. So would those be problematic?
Say that again. Advanced features like
triggers, for example, like or like other types of advanced features and triggers or things like that, database-based features, for example. Would these be problematic for you, or would these be, or have you actually thought about things like that?
So for the most part, we assumed that we were only looking at like select, insert, update, okay, delete, because we weren't expecting anyone or like a user to try to start defining their own triggers.
Okay.
So our default case would be to just reject anything from the application that's attempting to, for example, create a trigger. Or
okay,
like drop a table, for example.
Makes sense. So the policy language, so you've actually defined a language, right? Or like how are policies defined?
The policies are just defined as a select string. So okay, those select policies that you saw before where I was using the database view, it's defined just like that in the so like this write policy here.
Okay.
The only difference would be instead of a 1, you would have a wildcard, and then you would expect to just fill out that wildcard whenever the application or a user connects to the application.
Right. So it means that the learning curve is actually would be okay for developers, yes, right? Because they wouldn't have to learn.
It's very intuitive because you're like, well, let me just identify the rows just as before of what they should be allowed to access or add to the database.
Do you have any plans for releasing this? Another discussion point was like, the performance looks good, but can other people try to verify this?
Yeah, so there are plans to release it. We're still working on cleaning up the code. And then once we get that all done and remove like whatever miscellaneous comments I added, we'll be able to release it on open source it.
Okay, great. All right, let's thank the speaker again.